To say that it's a privilege to open an event, usually it's a platitude, but not today. My name is Zsuzsanna Pato, and I would like to welcome all of you on behalf of the two organizers, REP and REKK. Special thanks to our speakers today, Mike Hogan from REP and Bernard Malfliet from Elia, which is the Belgian TSO. We convened this event to learn a bit more about two recent power system events that place the issue of power system reliability into the spotlight. The first one is the outages caused by a winter spell in February in the US. The second one is the system split in Continental Europe in January also this year. The aim of today's event is to go beyond the headlines and often the blame games. What actually happened in these two cases and what needs to be done to avert similar cases, events in the future. Whenever we think about power system reliability, we should always think about that it always comes at a cost. So if you want to do an optimal level of reliability at the lowest cost, we should think always beyond simply investing into the supply infrastructure, let it be generation or network, and always a bit think about the demand options as well. A few things about the house rules. This platform doesn't allow you to intervene orally, so whenever you have questions or comments, please put it in the chat box, including questions of clarification. And the speakers will try to answer these questions either in a written form during the presentation or during the event, or we will have a Q&A session at the end. So we will choose about the questions and the comments, and we will discuss it in the last bit of this meeting. With that said, I would like to give the floor to our first speaker, Mike. Mike, the screen is yours. Thanks very much.
Okay, can you see my screen?
Yes, we can see your screen.
Okay, good. Good afternoon, everyone. Thank you for having me present on this topic. As most of you are well aware, there was a reliability event in the Texas or Ercot market in mid-February, which has led to a lot of speculation as to what happened and what to do about it, both inside and outside of Texas, both inside and outside the US. So we'll, in the time allowed, we'll try to dig into what the answers might be. So it was a weather event. It was an extreme weather event, and I guess the first question is, how extreme was it? Where does it fit in a statistical probabilistic analysis of what planners should be looking at and what is economic to do in response? So this looks at, you will have heard some discussion of a smaller event that occurred in February of 2011. And this looks at the duration and the depth of those two events. And as you can see, the February event of this year was both more severe and more sustained than the event in February 2011, considerably more sustained, almost twice as many hours below freezing, for instance, in Austin, as was the case in 2011. The question is, as well, was 2011 the only comparable to look at? This is a slightly different set of data from NOAA, the National Oceanic and Atmospheric Administration, that looks at past temperature events in Texas. As you can see, if we look past February 2011, which really wasn't that comparable, we can look to 1989, December. We can look to January of 1949, and we can look to January of 1930 and February of 1895. So the suggestion, I mean, I'm no meteorologist, but the suggestion is that this was perhaps a 25 to 30-year storm, at least historically. And it's also worth noting, and we won't get into this, I won't get into this in the presentation, but it's worth noting that this wasn't just a Texas event, of course. This was a severe, extended winter, very deep winter storm that swept across the entire Midwestern part of the North American continent. And there were impacts further north. There were load curtailments in virtually all of the systems up and down the Midwest. But they were less severe for the very simple reason that, of course, the further north you go, Texas is at the very southern end of that range. The further north you go, the more accustomed they are to seeing these sorts of conditions, and therefore the more likely you are to see investment in stronger winterization, measures. So it was not an unprecedented weather event, but it was statistically rare historically. A very good question is whether it will be less rare in the future and how much less rare. So the event was precipitated by a very, on the face of it, a very simple cause, which was a very sudden and extreme loss of generation resources over the middle of the night between the 14th and 15th of February. As you can see here, there was a loss of, within a few hours, of over 20,000 megawatts of generation on a system that has about 82,000 megawatts of firm generation. There was a significant portion of that in gross terms was gas-fired generation. There was quite a bit of wind that was out of service and had been out of service as a result of a lesser freeze-up event that occurred in the week prior. And there was some additional wind turbines taken out of service. There was also about 40% of the coal fleet that went offline in those early morning hours of the 15th. And then one of the 4 nuclear units in Texas went offline the morning of the 15th. The important question really is, what was Ercot's plan for a severe winter event? What we see here is that plan depicted very simply. The base case before expected outages was that they would have 82 gigawatts of available supply resources, 90% of which were thermal generation. Texas has, as some of you will be aware, the largest fleet of wind generation in the US. But their winter plan assumes that most of it is not available on days such as this, due to a combination of freeze-ups and low wind conditions. And so they were only counting on about 6 to 7 gigawatts of wind at the time, and some coal and some nuclear. And the normal peak in Ercot at that time of the year is 58 gigawatts. Their extreme plan, or their extreme scenario, projected a possibility of 67 gigawatts of demand, and then they factored in expected outages. So they projected having, both they and NERC projected having sufficient resources to deal with an extreme winter event. What actually happened? Well, the estimated peak was not 67 gigawatts, it was 77 gigawatts. And instead of having about 73 gigawatts of generation available after planned outages or expected outages, they had less than half of that available, less than 50 gigawatts. And as you can see here, most of the outages, the great majority of the outages, were among gas-fired generation, about a 40% outage rate, as I said, from coal, about a 25% outage rate in the nuclear fleet, and on average, about a 50% of the small amount of expected wind was unavailable. Their low wind contingency event scenario was 2 gigawatts, and they exceeded that in most hours during the event. As bad as the situation was in Texas during that week, it could have been much, much worse. This is what was happening to frequency in the early morning hours of February 15th. You can see, as in parallel with the rapid loss of generation resources, the rapid decline in frequency. And Ercot has said that they were within 4.5 minutes of having to dump the entire system altogether, which could have taken weeks to recover from. So as bad as it was, it could have been much worse without the load sheds that were ordered by Ercot. And of course, Ercot does not have any control over distribution system operators or retailers. So the instructions were to the retail operators, who then implemented them as they had prepared to do. This was the amount of load shed during the event over the course of 4 days. It is significant. It's 20 gigawatts out of a total of 77 gigawatts of projected demand on average, or peak demand, on average projected of about 65 gigawatts of demand through the course of the week. So it was a significant event, and it was not only was it 20 gigawatts, but it was sustained. It was about 70 hours of continuous curtailment of load at various levels. In 2011, that was about 7 hours. The piece that you don't hear discussed as much is what happened to gas production and the upstream gas situation. In the course of this week, production in the south central region of North America, the mid-continent region, fell by as much as 50% in the course of the event, which meant that about 7% of total US gas production was offline during the event. More importantly, much of that was well underway long before Ercot ever issued a first load shed notice. What you see here is the darker gray line is gas prices at the OGT hub, which is actually just north of Texas in Oklahoma. And the lighter blue line is gas production. And in fact, production had begun to decline precipitously days before the first load shed notice from Ercot, and gas prices had begun to rise exponentially. They actually, from a normal price range of $2 to $4 a million BTUs, or 1,000 cubic feet, they rose to as much as $900 per MCF at the OGT hub, $400 to $500 per MCF in Texas hubs. So, contrary to what you'll hear from some commentators, the dramatic loss of upstream gas infrastructure during this event was itself not precipitated by curtailment of electricity supplies to critical gas facilities. That certainly compounded the problem, but it had begun long before any curtailment notices were issued. So, as we'll see shortly, this was, in very many respects, a natural gas event before it was an electricity event. There are lots of opinions about what happened, most of them incorrect. This is a typical news headline following the event. Governor of Texas, who was in a great hurry to get on Fox News and pronounce this as being a failure of renewables, actually knew of the natural gas shortages that were occurring and that were accelerating days before any blackouts were issued, but he blamed it wind anyway. And this was fairly typical of reactions both during and following the event. So it's worth looking at some of the things that did not happen, despite claims to the contrary. This was not caused by reliance on wind. As we've seen already from the data, the Texas grid was as planned during such events, was overwhelmingly reliant on thermal generation, and only a small amount of wind was in the plan. But it did illustrate the remaining challenge that we face of replacing the role that fossil fuel generation continues to play in such circumstances. And of course, that can precipitate a conversation about the use of green hydrogen as the transition to the use of green hydrogen as a fuel for thermal generation that is available during similar circumstances. There was certainly no shortage of firm capacity during this event. The Ercot plan, even with expected outages, would have been sufficient to get through the event with a relatively manageable level of disruption to supply. Again, as I noted earlier, this was a 25 to 30-year storm. No prudent system operator would invest on the assumption that they would plan to get through that rare and severe weather event with zero disruption whatsoever. Rolling load curtailments, relatively short duration, would be normally expected for some small amount of load. In fact, that's what occurred during the February 2011 event. What there was a shortage of was cross-sectoral planning and, of course, a shortage of fossil gas. Certainly ERCOT had a role to play in that. In retrospect, there's clearly work to be done on ERCOT doing a better job of assessing just how firm their firm dispatchable capacity resources are. And again, that implicates the extreme level of reliance that Texas and some other systems have increasingly on fossil gas. The specifics of the Ercot market design had nothing to do with this event. As I said, there was sufficient investment. There was as much investment as a prudent system operator would expect to make in thermal generation as well as renewables generation in order to endure an event like this with an acceptable level of load disruption. All markets, including capacity markets, rely on prudent foresight. And prudent foresight was what was lacking from the regulator on down. Implementing mechanisms and forcing consumers to pay for them that would have thrown more money at more gas-fired generation, built to the same winterization standards as all of the existing gas-fired generation in Texas, and exposed to the same vulnerabilities in the upstream fossil gas infrastructure would have done no one any good, and would do no one any good in the future for a similar event. And it's worth noting as well that the winterization practices of generators in the Texas market are practices that extend back for many decades, long before the organization of a competitive wholesale market in Texas. It is simply a region that has not been accustomed to frequent exposure to these sorts of conditions, and so most Texas power plants going back to the 1950s have been constructed with turbine halls more or less out of doors, exposed to the elements. And the same is true of the natural gas infrastructure. Very little investment in winterization of production facilities, gas treatment facilities, gas processing facilities, and compressor stations on gas pipelines. Many of you will be aware that the Ercot market, which covers most, though not all, of Texas, is electrically isolated from the rest of the North American grid. It is connected only by, I believe, 4 HVDC interconnects with the Western and Eastern interconnects, North American interconnects, and 1 DC connection to the Mexico grid. And many people have pointed to that isolation, that electrical isolation, as having been a factor in this case. That's not really all that valid an observation. There were curtailments in all of the neighboring systems, and so there was not much available to help Texas out because everybody was struggling with the same winter storm. But it is still the case, and many have pointed this out, that more regional integration of the Ercot market into with neighboring systems would certainly be beneficial for Ercot consumers. And that's not something to be overlooked. But again, it was not a major contributing factor in this event. So where did it all go wrong? If those weren't the causes, what were the causes? What happened? Well, it was winter. That sounds like a frivolous observation. If you think back to the weather data that I presented at the beginning of the presentation, and remember that all of the precedent events that were comparable in severity were during the winter season, which is interesting because, as many people will know, the Texas grid is exquisitely tuned to be able to reliably supply demand during the brutally hot summer Texas peak demand events. And system peak has always been during summer in Ercot, still is. Very extensive, obviously, penetration of air conditioning combined with a very low efficiency building stock. The problem is that that the provisions that are made to, including in the market design, to make sure that the system is as reliable as necessary or desirable during the brutal summer peaks, it turns out during severe winter events are simply not up to the job. And we'll see that as I go through some of the other points here. The simple and ridiculous fact is that there's a fairly strict reliability regime that surrounds the electricity grid in North America. It's administered by both the reliability organizations that are regional in nature, as well as by the North American Electric Reliability Corporation, which is tasked with the job of assessing and enforcing reliability standards in the electricity grid, at least at the wholesale level. There is no parallel regime for the natural gas infrastructure. And in Ercot, which is primarily state regulated rather than federally regulated, the level of regulation, first of all, regulation is not done by the same regulator as regulates the electricity system, the Public Utility Commission of Texas. The gas system is regulated by the Texas Railroad Commission. Don't ask me to explain that. And they are appointed by the governor and are essentially hacks for the oil and gas industry. The regulatory regime for fossil gas in Texas is extremely weak. Both of those together add up to what was a very foreseeable gas supply failure during such an event. And it remains to be seen whether or not there was actually market manipulation by gas producers. There's been a lot of discussion of the fact that there's been a lot of transition of gas infrastructures, particularly gas compressors along the pipelines, from gas-fired compression to electric compressors, but also a lot of infrastructure in the gas processing sector as well as the production sector that were not identified as critical loads to be protected during a load shed event such as what took place. And that's, as I already discussed, while the load curtailments that affected those facilities compounded a problem, the problem they compounded had been underway well before any load curtailments were issued. However, it certainly would have been extremely helpful had those infrastructure facilities been identified by the industry itself and by the distribution system operators that serve them as critical infrastructure to be protected. There was an effort a number of years ago to get the regulator to require the gas producers to identify critical infrastructure, and the producers and processors successfully pushed back against the relatively simple requirement, which would have required them to fill out a 3-page form. So you can look back to point number 2, the weak regulatory regime of the fossil gas industry. As in the PJM market in the Mid-Atlantic in 2014, which has a capacity market, The mechanisms to pay for reserves, which in Ercot is an operating reserve demand curve, were compromised by the system operator's undue reliance on what turned out to be very vulnerable thermal generation. I talked about the very high peak load compared to Ercot's extreme scenario. What we've seen in Texas is a building boom. Since the 2011 event, more new residential housing units have been built in Texas than in the next two states combined, California and Florida. You combine that with the widespread use of resistance electric heating. 50 years ago, something like 7% of Texas homes were heated by resistance electric heating. Today, 67% of Texas homes are heated with electric resistance heat, including nearly all of the new residential units built since 2010. And then add in the rare but predictable storm, and what you ended up with was a very foreseeable winter load bomb, as I've referred to it, that nonetheless no one foresaw. There's been some discussion in some forums at FERC and elsewhere of the fact that Texas in particular has very large undifferentiated distribution circuits. And so those circuits that had protected loads on them, hospitals, fire stations, whatever, had a lot of other load that certainly could have and should have been able to be included in rolling load curtailments, but they were not available because they were on these large undifferentiated circuits. So what could have been a less severe event with rolling curtailments rather than a sustained 70-hour curtailment, rolling curtailments of smaller amounts of load turned out to be very different. And this has been referred to as sectionalization, and certainly work can be done over in coming years to change the topology of the distribution system so that protected critical loads can be on smaller, more isolated circuits, leaving more load available for the system operators and distribution system operators to implement rolling curtailments. Ercot, the state of Texas has one of the worst building efficiency performance ratings of any state in the country. And when you combine that with electric resistance heating, what you end up with is a housing stock that has very low resilience to extended disruption. So residences that could have remained habitable for 3 to 4 days, in the best case, became uninhabitable within hours. And finally, the Ercot market does actually have a circuit breaker, and we can get into this in the Q&A session. It does have a circuit breaker that is designed to alleviate scarcity pricing once you've reached a point where the responses, market responses and market incentives that scarcity pricing is meant to provide have basically been exhausted. But the Ercot circuit breaker, again, going back to the first point, it was winter. The Ercot circuit breaker is designed very much around summer conditions, including summer gas market conditions. And as a result, it failed to do what it was meant to do during this event, which meant that instead of scarcity pricing persisting through probably Wednesday night, would have been the point at which a rational circuit breaker would have kicked in. It continued through Friday morning, resulting in an extreme amount of pain for many players, both on the supply side and the demand side, much of it being unnecessary and pointless. So that's a quick run through, 25 minutes of what happened in Texas in February of 2021 and what some of the lessons learned are as a result of it and what didn't happen in Texas in February of 2021. And I'll turn it over to Bernard to talk about what happened in Europe. Thank you.
Thank you very much, Mike, for your presentation. It was really nice. I think the order now is that now we give the floor to Bernard Malfliet, who is head of operation at Elia in Brussels, and he will tell about another thing which happened in Europe, and he will introduce what happened on the 8th of January in 2021, the European system. So Bernard, please, the floor is yours.
Okay, good afternoon, everybody. So my name is Bernard Malfliet. I'm here for ENTSO-E, which is the community of all TSOs in Europe. And we have prepared a full detailed analysis of what happened on the 8th of January, where we had a split of the European system. So the system split in two, and purpose now is to explain how this could happen and what happened afterwards, and how we managed to make the system safe again very quickly as European TSOs. So I will show you the system state as it was before the separation of the grid. Already in out of focus, you see behind where the split was. So it's the Balkan area plus Turkey, which was split apart from the rest of continental Europe. There's the sequence of events, then what happened after the separation. We are going to look at the causes for the incident and related to that some conclusions, and I think from the causes we can already say what kind of recommendations there are to mitigate the causes of the system. So yeah, this is a very technical slide. I will pass quickly. This is just to show that we had a complete analysis of the continental European system even until Portugal in the middle of the screen on the right side graph. On the left side graph, you have a zoom in on the Balkan area and the flows that were going through the area. In blue, you have the market schedules that were foreseen just before 2 o'clock, and in red, the real-time power flow just before 2 o'clock. The differences between the two, this is remarkable, were not very different, but of course they are always a bit different. I think in particular I could, for instance, show that the flow here from Bosnia to Croatia was much higher in real time than the market schedule, and also the flow from Croatia HR to HU Hungary was also higher than foreseen. Also the flow from RS, which is Serbia, to HR Croatia was a bit higher than in the market schedules. But in general, not really very big differences between schedules and real time. Okay, what happened in local flows? Well, we see here a little bit of map where we see the biggest generation centers in this grid and the biggest load centers, and already in a line in the middle, a blue interrupted line, we see where the split is going to occur. So it's really going to block, going to stop all these exports from these big generation units towards the north, towards the rest of Europe. Physical exchange at that line was about 3,900 megawatts at the moment of separation. Physical exchange at the borders, sorry, at the borders of the grid. At the break line, the physical exchange was higher. I could have a long explanation why it is higher, but in general, such a technical explanation will always show that the break line will occur where the exchange is the highest. And so it is normal that the break line has the highest exchange possible. Lines tend to disconnect where they are transporting the most power. So this is where the break occurs. So there was about 5,800 megawatt exchange across the break line. The topology then maybe focused on Ernesti Novo. So we have a substation in Croatia, which is in normal operation, having two lines here connected to one bus bar, and two other lines here, Mitrovica, Uvijek, are connected to the other bus bar. and you have PEX1 and Zerjavinec, which are connected to the first bus bar. This is a normal operational situation, but unfortunately, at the time of the split, the maximum power went into the substation from the two lines on the right and went out of the substation from the two lines on the left. So this means that the importing lines into the substation were on one bus bar, the outgoing lines were on the other substation. So in this particular situation, and I really have to insist on that because it was not normal. Normally, the power flows are otherwise managed, but in this particular situation, the whole power flow went through the busbar coupler. And so the busbar coupler indeed, and this can show, I think on one of the next slides, yeah, here, this is the power flow going through the busbar coupler, which was already, at 12 o'clock, it was very low, and that between 12 and 1 in the afternoon, it started going up until around 1500. And it started ringing bells that, okay, we have to take care that this flow does not go too high. And so we see here the protection setting, which is the top line, and the second alarm setting, which is the second line. And here we see that the busbar coupler disconnected a little bit before, the measurement was still at the second alarm, while apparently in reality the flow was already at the protection setting. So yeah, a little measurement error here. So the equipment using another measurement value, the protection equipment is of course looking at the signal, the 50 Hz signal, while the measurement in the dispatching is a measurement which is refreshed every 2 to 4 seconds, and it's not, of course, exactly the same value at all times. So the busbar coupler disconnected and effectively cut the complete flow coming in from Bosnia and Serbia and going towards the north of Croatia and Hungary. This flow was completely separated, so meaning that all the lines dropped almost to zero after the disconnection of the busbar coupler, and this flow has to be redistributed over other lines. And then you see what happens. So at 14:04:25, this line disconnects. This busbar coupler disconnect, number one. Then number two, you have at 14:04:48, you have a line in Serbia which was not supposed to be overloaded, but then in reality it turned out to be overloaded. It turned out to take more flow than was originally estimated and calculated, and so this line went into overload, and a 20-second relay disconnected the line Novi Sad-Subotica. Of course, then there are already two important lines transporting power to the rest of Europe from the Balkan area, which are disconnected. And this led then to further disconnections of plenty of other lines, most of which were disconnected due to distance protections. Now, distance protections are protections that safeguard us from short circuit flows. So flows which are too high for the equipment, which have to be cut as quickly as possible. So all these lines, in a way, detected short circuits which were not really there, but I will come to that because all this is a consequence from the loss of stability between the two areas. So all these lines afterwards, number 3, number 4, to the east, to the east, yeah, and then to the west, 5, 6, 7. In the east, in Romania, number 8, and then Croatia, number 9. And so on, 10, 11, 12, 13, 14, 14 lines disconnecting, and which effectively splits the grid into two parts. Now, why do all these lines disconnect? Well, this is because of a voltage phase difference which occurs. So what we saw already before the incident happening was that there was about 60 degrees difference between the the northwest and the southeast parts of Europe. 60 degrees is quite a lot because 90 degrees is the maximum that we can really manage before we go into instability. With an angle difference of more than 90 degrees, this is like here on the top of the hill. As long as you are below the 90 degrees, here on the bottom right of the slide, you have this small drawing. As long as you are below the hill, you can still drop back to the 0 degrees or to smaller degrees. As soon as you pass over the 90 degrees point, you go to the point of instability. And this is something that happens very quickly. And so we lost the first line, the coupler in Ernestinovo. So the degrees went up from 60 to 75, something like that. And then when we lost the line from Subotica Novi Sad in Serbia, we passed the 90 degrees limit, and the two systems started to oscillate, one compared to the other. So they were not in synchronism anymore. So where we usually have the whole continental Europe system, so the whole map completely synchronized, and so at exactly the same frequency, the south-east part of Europe started oscillating compared to the north-west part. And this oscillation is very dangerous, because this oscillation will be seen by load, this will be seen by generation, and so if this takes too long, then all generators will start to disconnect, load will start to disconnect. So luckily we have all these distance protections, and these distance protections, because of the oscillation, started seeing very high currents and very low voltages. And so because of that, they disconnected the lines. And so luckily they did it, and they will always do it, and they will continue to do it, and we will never take these protections out, because this is exactly what you have to do. As soon as the system starts oscillating, you have to split it. This is the only way to create again a stable system, and indeed, immediately after the split, both systems became stable again almost immediately. Voilà. So here you see some graphs of exactly what happened, and the phase angle graph is quite impressive, of course, where you see that it really the system is completely unstable. Starting where the split happens. You also see here the frequencies that on the one side the frequency went down very quickly, on the other side the frequency went up very quickly, because exactly the split happens at the maximum exchange, and so this complete exchange is interrupted, meaning that in the south western parts of the southeastern parts of Europe, there is 5,900 megawatts too much generation compared to loads, and in the northeast part there is 5,000 megawatts too much loads compared to generation. And so immediately the frequency reacts because this overload, this high load or this high generation has to be compensated with kinetic energy of the running machines. So the frequency goes up very quickly in the Balkan area and goes down very quickly in the rest of Europe. So we have two areas. And so directly after the split, this phase angle stabilized immediately. And so the biggest interruptions that we had was that in Romania we had some loss of load locally. So some distance protections reacted that maybe should not necessarily have reacted, but okay, we are happy that they reacted because they realized the system split, but some load was lost because of this. And another reaction was that because of the oscillation also, and the effect of it was that we lost the HVDC connection between France and Spain. So those were the two important results. And this is very little. It could have been much worse. If this oscillation had lasted, instead of a few seconds, had lasted 10, 20, 30 seconds, we might have lost the whole of the Balkan area, and then a lot of generation and loads in the rest of Europe as well. So it could have been much worse, but luckily these distance protections managed to split the system very quickly, and the system stabilized very quickly after the interruption. So afterwards, what do we see? Well, we see in the Balkan area, which is the top on the top right, stabilization after 15 seconds, thanks to the activation of frequency containment reserves, and also 975 automatic disconnection of generation, which also helped a lot to make the frequency not go up too high. And because there is indeed a risk that the frequency would go too high, and then all generation would disconnect from the grid, and again you would have a blackout. In the rest of Europe, the continental part of Europe, we had some automatic interruptible services. These are contractual loads which are contracted to be interrupted in case of extreme conditions, and this is indeed an extreme condition. So 1.7 gigawatts of load was disconnected in France and in Italy. We also had activation of frequency containment reserve. And there was also, and this is relatively new, there was a supportive action from Nordic and GB over the DC connectors. So we have installed since some time, I think a few years, we have installed frequency support on the DC cables between the synchronous areas, and this indeed helped a lot. So 447 megawatts from the north, 57 megawatts from GB. This, of course, can also run in the other directions. If the Nordic area has a need, then Continental Europe can also supply this supportive power, and same towards GB. Then afterwards, we had a reconnection about 1 hour later. So indeed, we had to go back, both areas had to go back as close as possible to 50 hertz in order to be in an as stable system as possible, which allows to reclose the lines without them taking again too much power immediately. So if the frequency is close to 50, means that the area is balanced, means that when you put the lines back into service, they will transport almost no power. So this is the best way to reconnect the system. And all this was coordinated in less than 1 hour, we could say. So a lot of coordination has happened in the western part. Amprion and Swissgrid are the normal leaders to take control of the system. And in the southeastern part, it was mainly EMS, the Serbian TSO, who took the lead to make sure that all TSOs coordinated to get the frequency back to 50. So the complete cost tree is maybe a bit too detailed, but we have put it in a little bit less difficult to read summary. So the system separation, in the end, it was because of a dynamic angular instability that happened. The angle became larger than 90 degrees. This angular instability was because of a very high power flow and a low stability margin in the area, and because of the loss of the first event and the second event. Those two events caused the dynamic angular instability together with the high power flow. First and second event, what can you say about that? Well, we need to look at the overcurrent protection concept. Is it a good way to connect a coupler and also in general a line at maximum power, or do you want to put the protection at higher values to avoid lines disconnecting too soon before you have the chance to react? We need to look at configuration of a substation topology. Is the topology in a substation always adequate, or does sometimes the topology need to be adapted to take into account the flows that are happening? And then subsidiary question is, how easy is it to change the topology of a substation? And there are rules about that, and then some of these rules in several TSOs state that you cannot change the topology without somebody in the substation doing a visual check. So that means then that you cannot immediately change the topology. You have to take your time to change the topology. We need to look at the application of the N-1 security calculation, and especially across borders. Inside the countries, everything seems to be going very good, but it's across borders that we need to check if N-1 is really calculated everywhere in a sufficiently detailed way. I think there are agreed lists that have been approved by regulators, but maybe in the light of this event, we have to take a look at these lists again, if these lists are really complete in terms of N-1. We need to look at alarm handling. Okay, we put hops here, but I think it's more in general. We need to have more general rules on when we need to start reacting to alarms. If a busbar coupler in this case, or a line is loaded 80%, is that okay, or do we need to start reacting to it at 90%? We really need to react, and at 100%, yeah, there is a protection and it is connected, then it is too late, of course. So I think those are the most important things that we want to look at. So to see the protections, the topology, the calculations, and the alarm handling. Those are the really main topics that we are going to develop in our recommendations. Some other critical factors which will lead to recommendations. There was a change of flow before the initial event. We saw that just before the disconnection happened, the flow went up from the Balkan area to the rest of Europe and also through the coupler. There is some imbalance there that has been generated because the flow was higher than the schedule. So we need to check where this imbalance is coming from. It is normal that there is imbalance. There is always imbalance in the system, in a large system like Continental Europe. But in this case, it led to an overload, and so we need to check if we can control better these imbalances. Have a look at regional capacity calculation, if this can help to better see the consequences of anything that happens, of any element disconnecting from the grid, so regional security analysis. After system separation, there are several things that we have to take a look at. If we have a European-wide system of netting of imbalances, which is IGCC, which allows one country to net its imbalance with another country. If, for instance, France is 100 megawatts too much and Germany is 100 megawatts too little, this can be netted, and both countries are then immediately stable thanks to IGCC. Of course, netting should not happen when the system is split, because then you would have the adverse effect, and you would start netting imbalances over a split system, which could make the situation even worse. We need to take a look at load frequency control, if it's really working, how it should work during a system separation, if it should stay in normal mode or in frequency mode or something like that. So this is going to be analyzed. Frequency support is going to be further analyzed between the different synchronous areas. I think we can further optimize this, but as I said, it already worked very well. Data representation in EAS. Already the 8th of January shows that the EAS works very well. The EAS is a European awareness system. This is a system which exchanges data between all European TSOs in real time. And so the system is available in all the different dispatchings to show the real-time situation of the grid. And this helps us a lot to see that there was a split, because without the system in a country like, for instance, Belgium, far away from the Balkan, you would just see the frequency go down but have no clue about what is happening. So thanks to the EAS, you see, okay, there is a problem there, because I see that the frequency in the southeast is going up and the frequency in the rest of Europe is going down. So probably we have a split. We're going to see about communication with TSO, if we can further improve this. I think it already worked very well, given that we managed to be connected within 1 hour, but it can always be better. The coordinated executions of measures, of course, so we need to get all TSOs involved in the measures that need to be taken in order to reconnect the system when you have such a serious situation. And so we're going to elaborate further on the procedure that already exists, but we're going to elaborate it further, the procedure of system separation and resynchronization. Then very quickly also the conclusions, but I think I said the most there. So the system separation led to 2 electrical islands. There was a very fast stabilization after the split, thanks to a lot of automatic measures, but also further manual measures, which helped bring the frequency back to 50. We think the incident was handled quite well, that the consequences were very limited. They were not zero, but they were very limited. And of course, we are doing further evaluation and derivation of recommendations. This is still ongoing. That's why I could not give too much detail on the recommendations, because the work is still ongoing. It's going to end in June, normally with ACER and with NRAs, which is an official process. So we don't want to short circuit that. The recommendations will come when we have agreed them with ACER and the regulators. It is a warning. It is a warning for resilience again, future challenges. It is a warning that instabilities can occur in the system. that transfer of power is not infinite. So we saw 5,900 megawatt exchange with the Balkan area, and then yeah, not a simple outage, but an outage followed by an overload, which then automatically had the outage again, which caused the system to become unstable. So we were very close to instability. So we have to take care still about stability limits in Europe. So not it is clear from this that giving 100% of the capacity to the market is good in theory, but in practice you have to take care about the limitations of the system. So that is the main message that I have for today. It's still work in progress, but soon we will be ready with the final report.
Thank you very much, Bernard, for the presentation, and as well for Mike for the presentation. I think they were very interesting ones. And we can start now, I think, the question and answer session. We have received 3 questions, and I do not pose them directly, but maybe I do some translation from that. So what you have to know is that I'm László Szabó, director of REKK, and I'm not a technical people, I'm an economist. So maybe some of the question will reflect this less of a knowledge on the technical issues, but really thank you very much for the information which you were provided. And then going to the questions and to my translation to the question, I put the first one as like this, is that what I understand from the presentations is that we have 2 events which happened, maybe that's the thing which is in common, that it happens in this winter time, and both of them affected the power system in Texas and in the European system as well. But we see high differences because what we know about the system is that the Texas system is an isolated one. The European system is a very connected system on the one hand. On the other hand, what we can see is that there are, in spite of these differences, there are similarities in the system. Of course, winter weather will change more dramatically or more volatilely in both of the continents, so in the US and in Europe as well. We see at the same time that volatile renewable production will come in both systems with higher level in the future. And we see at the same time that gas is an important source of electricity production in both systems. So we see these differences and the similarities. And the question is whether we can learn, and what can we learn in Europe from the Texas event? And I know, Mike, that you are an expert in both continents, so you not only know the US systems, amongst them the Texas one, but you are quite familiar with the European power system, their operation and regulation as well. So what would be the main takeaways according to your knowledge and information what you have from the Texas system event?
Well, I'm not sure I'd say I'm an expert in both. You can know a lot about a little or a little about a lot, and I know a little about a lot. So lessons for Europe from the Texas event. Well, a lot of people in Europe thought one of the lessons from the Texas event was that there's a problem with being too reliant on wind and solar. And that certainly was not a lesson to be learned from the Texas event. Texas was not in the event terribly reliant on wind at all. It was very reliant on natural gas. One of the, I guess, so moving on, expanding on that point, one of the failures that we saw not just in Texas in February of this year, but we saw in California in August of last year and in PJM in the winter of 2014, is that regardless of how one designs mechanisms to ensure that there are sufficient resources available under various sets of circumstances, whether it's a capacity market or it's Texas-style administrative scarcity pricing or co-optimization as in Australia, it only works if the assessment by market authorities of how firm resources are is a valid assessment. So what we found out in PJM in 2014, Texas of this year, was that having investment in thermal dispatchable generating capacity only gets you so far. If the provisions that are in place for the transmission system to which it's connected, or the fuel supply and transportation arrangements upon which it relies are not as secure as you're assuming they are, then your planning process for the ability of the system to survive events such as this is not going to work. So this, you know, I'm personally a proponent of market solutions. I'm a big proponent of the organized markets that have been established in most of the North American system and across Europe, but they do not substitute for prudent planning. They do not substitute for sound regulation of system codes, of competition, of safety. They do not substitute for robust administrative oversight of reliability standards, both in the power system itself and in the upstream and downstream networks upon which it relies. And then certainly there are the lessons associated with the role that too much reliance on resistance electric heating can play in extreme winter events. There are lessons to be learned in terms of the role that poor building efficiency performance played in lowering the resilience of the demand side to disruptions. And there will always be disruptions, no matter how good your planning process is and how good your market design is. There's one more that I was thinking. I mean, certainly we need to be thinking about whether the historical patterns of extreme weather are likely to continue into the future, or whether we need to be planning on more frequent extreme weather events. I'll think of the other one in a minute, but I'll let Bernard offer his observations.
Bernard, anything from your side to this question?
It's yeah, difficult to say, but I think we have certainly processes in place in Europe to deal with adequacy. So to check in advance when we can expect that there are adequacy issues. So we have these mechanisms now that every week all countries have to declare what their positions are going to be for the next week, what they expect as availability in terms of generation, and what the load is going to be. So this can give you a picture whether some countries or plenty of countries have a shortage, but this still does not prepare you for the extreme situations. So we try to prepare for the extreme, but it's really the 1 in 10 or the 1 in 20 years that we look at. So we know that when some countries are short, that they tend to offer a weekly insight in what the temperature predictions are for the next week and if they're expecting problems or not. So there is quite some coordination already in Europe. Does this mean that things like this cannot happen? I don't think so. It can still happen in very extreme situations, like what happened in Texas. This is out of the ordinary. So this is very cold, a lot of wind. So yeah, in theory, it could happen in Europe, which we hope that we are prepared for it indeed, so that we have sufficient processes in place to manage it. We will at least see it coming. That's the least. So it should not be a surprise.
Yeah, and at some point, you know, at some point you're dealing with mitigation, not prevention, right? At some point in the severity of these events, you have to accept that there will be some disruptions. And one of the lessons, you know, there's some lessons from Texas about being better positioned to handle that. I mentioned the fact that that the protected loads, you know, critical load, tended to be on very large undifferentiated circuits, which really handcuffed the system operators from being able to be more selective and to significantly reduce the severity of the event. And so that's a lesson learned. Certainly, the resilience of buildings is a mitigation issue, not a prevention issue. One that I forgot that is a lesson worth learning is the importance. If one is going to accept the importance, and I do accept the importance of administrative scarcity pricing in the proper operation of the energy and ancillary services markets, it's also important for one to look at some sort of circuit breaker so that in the event of an extended crisis, what occurred in February, the level of scarcity pricing can be moderated once you reach a cumulative impact that has achieved the incentives that it's designed to achieve. And that didn't happen in Texas. Again, because it was the mechanism that was in place was designed around summer peak conditions and really doesn't work well in winter peak conditions.
Thank you. Thank you very much for the answers. And maybe we can move to a second area, which I would call processes, because what we have in Europe, we call it the resource adequacy planning. And of course, you had some planning in the Texas system as well. And how do you see the main differences, Mike? And do you think that the European resource adequacy planning is working better, working differently, or should be improved? And what should happen to the Texas planning system as well?
If you look narrowly at the question of capacity planning, generation investment planning, the one could conclude actually that Texas in particular and the North American organized markets in general are further along, given the fact that you know the resource adequacy processes for organized markets have been evolving in most North American markets since the late 1990s. And in fact, again, as I noted in my presentation, strictly on the basis of investment in generation, the Texas planning system, the Ercot planning system, could be said to work well. The market mechanism worked well. There was sufficient investment in generation that really should have been available to operate during this event. Where the planning process, and in Europe, the resource adequacy planning process, assessment process, and the mechanisms for ensuring resource adequacy are still very much a mixed bag. They are member state by member state. By and large, there's the Clean Energy for All package provided for a European resource adequacy assessment process that Bernard and the folks at ENTSO-E have been working on diligently. But there is this patchwork emerging of different kinds of forward capacity mechanisms, which I personally find very disturbing. And combined with a tendency to underemphasize full marginal cost pricing in the energy and ancillary services markets. But in terms of resource adequacy, again, the assessment process is different from one member state to the next, and it's different from one organized market region in North America to the next, to be fair. But it's still Bernard and I both talked about the fact that one needs to plan for and foresee situations where you're going to have to mitigate disruption rather than expect that you're going to avoid it altogether, simply because it's not economic to invest so much that even if you could, that you'll never experience disruptions. And unfortunately, in many member states in Europe, as well as in some of the regions of the US that are still traditionally vertically integrated, there's a tendency to respond to these situations by saying that this should never happen, that disruption in the system should never happen, and to overinvest in resource adequacy. The other point being that the nature of resource adequacy is changing as the profile of resources on the system continues to shift towards more and more variable resources. So as we saw in California in August of 2020, because of the very high penetration of solar in the California market, the load curtailments, and there were relatively minor load curtailments, but the supply-related load curtailments that occurred in California occurred not during the system peak demand hours of the late afternoon. They occurred during the evening ramp, when gross demand on the California system was down about 10% from where it had been during the peak a few hours earlier. But as solar solar production declined, they had not scheduled sufficient generating capacity. There was sufficient generating capacity connected to the system, but they had not scheduled sufficient generating capacity to address what turned out to be the net system load peak. And what that points to is the fact that just the nature of resource is changing, and it's less and less now about gross capacity connected to the system and more about the system's ability to respond to a much more flexible, much more dynamic, much more rapidly changing minute to minute, hour to hour reliability situation. So traditional focus, and we're seeing this in a lot of the organized markets in North America. And I think, personally, I have to say, I think Europe is going to start to learn the hard way that this traditional, very traditional focus on just the raw amount of firm capacity connected to the system is going to become less and less adequate to deal with the evolving resource adequacy challenges on systems.
Thank you, Mike. Bernard, anything to the question?
I'm not sure I can add to what I said earlier, and I think Mike was very good in his summary of everything that needs to be said about the European system. So indeed, so we as TSOs, we see also the effect of solar, which has really changed the peak point of the system. So the load used to be low during the night. Now it is low during the day, and because of all the rooftop solar. So this has really shifted the peak. So we need to the processes need to follow these changing conditions. That is true.
Okay. There was another question, and I wanted to ask as well that let's move next to the actions, I would call it. And under actions, I would rather mean the short-term solutions or fixes. So, Mike, what would be, in your opinion, or what are the short-term changes in the system which will come, or which are underway in Texas, and what are the longer-term solutions to this issue? Because we saw quite many things which were contributing to the event. So what are the short-term fixes and what are the real long-term solutions which you would foresee? And I just would like to point to one question which came from the audience, and it was asking that in 2011 you had a very similar event and recommendations were made there. And I don't know if these recommendations were realized or not. And the question is if the situation would change now, and if you would really go on the path to make the solutions or not. So how do you see this issue?
I think we need to hear from Bernard on this as regarding short-term actions in the European market, because as I think was evident from the two presentations, they really were two very different kinds of events.
Yes.
Which is not to say that both of them don't have lessons to be learned for both the North American systems and the European systems. In terms of the changes that are likely to happen in Texas as a result of the Texas event, that's a really good question. Because as you say, as the questioner from the audience pointed out, there was certainly a much less severe event in February of 2011 that nonetheless spawned a number of recommendations as to things that could mitigate a similar event in the future. And a lot of those actions have not taken place. The most obvious ones were the recommendations from NERC, North American Electric Reliability Corporation, and from various Texas experts to increase the amount of winterization on power plants themselves. And it remains to be seen what percentage of the very large amount of unavailability of gas-fired generating was due to the freeze-ups in the upstream gas infrastructure and what percentage was due to freeze-ups on the plants themselves, but certainly there was a large percentage of both and a lot of overlap. One of the big questions that comes out of the Texas event in terms of market design is, given the extreme economic incentives in the Texas market for demand and supply to respond under such circumstances, and best to be able to respond under such circumstances, why didn't generators themselves, regulation aside, why didn't generators themselves, especially following the 2011 event, invest in more winterization in order to be available during a period when actually they could have earned quite a bit of money? That's what the market is designed to do. And it's going to be an ongoing debate as to what needs to change. Personally, I think what needs to change, a very specific question, but both in Texas and in other systems around North America, and I think also in Europe, is that the planning process and the mechanisms that use that planning process to price the value of reliability reserves needs to be much more robust and much more disciplined in looking at all of the things that can affect the reliability of those resources, not just whether the plants themselves are winterized, although certainly that will be a lesson that we have to relearn again. We learned it to a lesser extent after 2011. We've just learned it the hard way again. But there are obviously other systems that are implicated, the natural gas infrastructure, the transmission system, even such simple matters as the fact that maintenance crews, because of a lack of winter preparedness on the highway system in Texas, maintenance crews for a couple of days weren't able to get out to the gas production facilities and to the power plants to address the frozen equipment. These are kind of, you start to get into a lot of very, very interesting kind of ancillary planning issues. So certainly more focus has to be on why the market incentives for investment in the ability to perform under situations like this didn't do what they were supposed to do. I would say, however, that calls that you've heard from various people for the implementation of a capacity market in Texas are frankly just silly because they missed the point. In fact, in PJM in 2014, which had a capacity market, has a capacity market, that capacity market failed in much the same way and for much the same reason. the planning process and the assessment process for how much of the capacity connected to the PJM system was actually firm failed. And as a result, the capacity market had procured a lot of capacity that simply didn't perform and had paid for it, paid dearly for it. And what PJM and ISO New England did in response following that event was actually to amend their capacity markets so that they paid out their compensation in much the same way the Ercot market pays out its compensation under reserve demand scarcity pricing, which is to concentrate all of the compensation and all of the penalties in those few hours when the system is at most stress. So the capacity market is certainly not the answer, but obviously the various scarcity pricing mechanisms, whether in the capacity markets in PJM or in the ORDC market in Texas, why they didn't work as intended. And that will be, and I think, again, it comes down to the planning process, the resource adequacy assessment process, and whether or not it's robust enough. And that's a regulatory and planning issue. It's not a market issue.
Thank you, Mike. Bernard, any further additions? There were a few comments from the audience that in Europe, what happened that actually it was not an outage. The system was had some disturbances, but not really a very severe situation. Will we learn, and will be there actions taken by ENTSO-E and by the TSOs?
So on the incident of the 8th of January, indeed, in the short term, what can you do in the short term? You can avoid the same. So you can try to avoid that the same thing happens again. So of course, in the short term, we have looked at the topology of the system close to where the incident happens to make sure that these overloads don't happen again. And we've been looking at alarm handling in the dispatching, and those are really the ones that you can do the quickest. And then the other recommendations are going to come later on. And so in the longer term, it's not avoiding the same, it's avoiding the similar. It's avoiding that something like this happens anywhere in the system. And so then it is transposing the solutions that you find locally, transposing it to the whole of Europe. So to look at all these recommendations in the whole of Europe. So I think this is something that we certainly have to look at. And another type of recommendations will go in the direction, okay, if it happens again, because it did happen already once in 2006, if I remember correctly, and then again this year, if such a split happens again, how do we make sure that also the next time everything goes well? So how do we make sure that all the processes are in place, that the systems remain stable, that the systems disconnect in a stable way, and that both frequencies stay within an acceptable range and go back to 50. So this is also something that we're going to work a lot on to make sure that the next time, first of all, to try to see if we can avoid the next time, and if we can't, that we make sure that the next time everything goes at least as well or maybe better. So that is in general what I think. If I may also think about what happened in Texas, indeed in Europe also, we will have to think about the future portfolio of power. It's going to be much more solar, much more wind, much less nuclear, of course. We need to see that we have a portfolio that is adequate 24/7, so that we always have the power to manage the load in any possible circumstance. And this is going to be a very interesting challenge. I firmly believe that we can go to a maximum amount of renewable, but we will need to manage the variability. So we will need to manage other means to I don't know what, maybe battery storage, maybe more hydro, if it is still possible. It's very difficult to say, but we will need to manage this adequacy question to make sure that at all time we can ensure sufficient power. And the other question is, and I think we saw that also, it is not that enough that the power is installed, it has to be available, it has to be there, it has to be running. So we have to make sure that we have the necessary procedures in place to be able to force, in a way, or to convince, or to have the right price signals. I'm not sure if it will be sufficient with price signals, but to convince market parties when the production units have to absolutely be connected to the system, and when we are really facing adequacy issues. So yeah, this is all still a big challenge for the coming 10, 20 years, I think.
I wanted to pick up on the last comment by Bernard, because I think it's very important. If you look, again, I've referenced the PJM and the New England action in response to the 2014 polar vortex event. Two things are worth taking away from that, I think. One is that of course PJM and ISO New England are much more accustomed to seeing severe winter weather. So the conditions that prevailed in Texas during the event in February are actually not that unusual for conditions in PJM and especially in New England. As a resident of New England, I can tell you that those kind of conditions are pretty normal, actually. It is much more economically rational for system planners, for system operators, for generators, and for the relevant customers to prepare, to invest in and prepare for events like that. Secondly, and connected with that, is that when PJM and ISO New England implemented these reforms to their capacity markets that turned them into much more sort of typical scarcity pricing mechanisms, the response was quite interesting, because the expectation by many people was that the response would be that gas-fired generators would go out and contract with the gas producers and pipeline companies for more firm supply transportation arrangements, which would have probably driven clearing prices in the capacity market up quite high because of the costs of those kinds of arrangements. What actually occurred as a result of the fact that they relied on market responses to augmented pricing signals rather than relying on command and control, such as requiring generators to contract for firm pipeline capacity. What actually happened was the gas-fired generators, many of them, invested in converting their units to be able to burn backup oil, distillate oil, stored on site in tanks for a period of hours or days, which of course firmed up their ability to respond under such as what occurred in Texas. And because that's a much more inexpensive and much more quickly implementable solution, PJM and ISO England now have a much more reliable thermal generating fleet during events like this, and they got it for a relatively low cost. So clearing prices in the capacity markets actually didn't go up very much at all. The question in Texas is going to be how much more frequent are events like this? Are they going to be frequent enough to justify investments? And are you going to direct investments in winterizing power plants, which is could actually be quite expensive? Or will you create conditions that drive generators to respond in ways that you may not necessarily anticipate, but that could address the problem at a much lower cost, similar to what happened in PJM and ISO?
Thank you, Mike. Just looking at the time, we might have still a few questions, I think, which we could answer. And I might turn to my next topic here is the gas markets, because you mentioned, and it was quite interesting for me, that in Texas, the gas markets are regulated by a different entity, and then probably there were not too much coordination between the power sector regulation and the gas market regulation. So when you are building up your electricity reliability assessment and so on, you might just count that, okay, the gas pipelines will work as they should work, so gas will have there, it will flow in. So how do you see the prospect there? Would it improve in the future? There will be more coordination between the two agencies, or what is the future there in the gas markets part?
Yeah, I mean, there certainly is a real dearth of cross-sectoral coordination between the gas market in Texas and the power market in Texas, and there's a dearth of robust resiliency regulation in the gas market, in the gas industry. It's hard to imagine that there won't be more coordination in the future. There already are calls, and there will be more activity in the area of designating critical gas production, gas processing, and gas transportation facilities as critical loads to be protected from curtailment, to make sure that they're on segregated circuits so that they don't drag a lot of other much more interruptible load with them. And remarkably, there were some critical upstream gas facilities that actually had participated in what Ercot calls emergency response service, which is to sign themselves up as interruptible load and get paid for that. So people are quite naturally asking, well, I think maybe in the future we shouldn't allow critical gas facilities to participate in the ERS program, which is a pretty obvious reform. But whether there's going to be real teeth applied directly to the upstream oil and gas industry in Texas by the oil and gas industry regulator is very much a political question. There's not a sitting senior politician in Texas that doesn't benefit from substantial financial support from the oil and gas industry. Whether or not there's going to be real serious reform of the reliability regime in the upstream gas industry, including a closer examination of when multiple regulation took place, that remains to be seen. I think we're likely to see a stronger response at the federal level outside of Texas, where the regulation of the upstream gas industry is much more the province of the FERC, the Federal Energy Regulatory Commission, and we'll see a lot of action there. But Texas likes to go its own way and has set things up in such a way that to a great extent they can go their own way. So we'll see how far it goes, and we'll see how much Texas electricity consumers are forced to pay for a lot of winterization in the power plant sector, and maybe even forced to pay for more capacity, which they don't really need, or not, at least not to address this situation, versus more directly addressing the root causes of the event, which in many cases were problems with the upstream gas industry. So we'll see. If Texas is a funny place when it comes to politics.
Thank you. Maybe a question, and then maybe we can start with Bernard this time. That what you mentioned is that we'll see more and more solar and wind generation in the system in the future, which means that, of course, more volatile production at the supply side. And in some studies, we have read that actually a very interesting situation is taking place on the demand side. And actually, as Mike mentioned, it happened quite quickly with a different technology, but with similar result, that you have now the heating from the 6% up to 67% in Texas, but like electric resistance heating. But what we foresee in Europe, and probably it will come in the US as well, that it will be not electric resistance heating, but electricity-based heating as well. So because we can use heat pumps and so on, which means that we are not only increasing the volatility on the supply side, but on the demand side as well for the power sector, because electric heating, even if it's heat pump, will really be very changeable in the future. So how do you see this issue? What do you think that what are the solution in that one, that we foresee this development, maybe not next year, but continuously growing to a quite interesting system of consumers who are consuming weather dependently, and then producers who will be really dependent on the weather as well. Bernard, maybe we change the order, and then you start, okay, and then Mike will come.
I will try to be short, because for as many people in the electricity business, there are as many opinions on what the future is going to be. So I really believe, I'm probably not the only one, that we need to make the consumption more controllable, more responsive to price signals, or and that's what I personally believe, more responsive to automatic systems which have been agreed in advance. I think we talk already a long time, for instance, about taking fridges out of service for 10 or 15 minutes when the frequency is low, to have the possibility to control when you are charging an electric vehicle. The heating is also something. You don't need to have heating 24 hours continuously active. You can take it out for 15 minutes if necessary. So you can really, in theory, you can manage the load really a lot, especially the domestic load. The industrial load is a little bit more difficult, but I think on the industry side already lots of efforts have also been done to stabilize their consumption. So yeah, and then everything needs to be complemented with systems, with battery type systems. So we already have a lot of hydro since a long time in Europe, which is a kind of a battery, and then we will add some modern batteries which are even higher performance and better to manage the variability of the generation. So I think, yeah, on the load, there is a lot that we could potentially do, much more than even more than we imagine today. I will leave it at that.
I enthusiastically agree with that. Now, I mean, heating is obviously a special challenge. I mean, electric vehicles are, easy in the sense, that most vehicles sit idle for 90% of the time, and so it's relatively easy to shift around when you charge them. Electric water, heat pump water heating is similar. You can shift around when you actually heat up the water, as long as there's enough water in the reservoir. Space heating really brings much more to the fore the importance of building efficiency performance. Because as Bernard said, with electric heat pump space heating, it is possible to preheat spaces. A lot of new commercial buildings are doing just that. But of course, the extent to which that can help is dependent on how efficient the building itself is. And so it's quite possible, very possible, in fact, it's been well demonstrated in pilot programs, that a combination of much better building efficiency performance with electric heat pump heating can turn building heat from a problem for the power system to part of the potential solution by making it a much more flexible load. But as Bernard said, I mean, there's across the landscape of demand, there's so much more that can be done to make load more responsive to variable supply without imposing inconvenience or discomfort on consumers.
Thank you. There was a question actually from the audience very connected to this one, where Jakub Groskowski was asking that, for example, in Germany, they are planning for 100% renewable system by 2030, which I'm not 100% sure, but something very close to that one for sure. And then he's asking whether we see this as is it the right speed of this change, because we have to take into account the storage for example, the battery storage and the hydrogen availability? Isn't it in the right balance that we are going really too quick in one and not quick enough in the other solution? Because of course, once you have the storage there and the hydrogen there, you can do these solutions, which is very nice. But if you are rushing too fast with your generation system, there might be too much of an imbalance. And I might just put into a small question to this one, and the question is that if we see this very quick change in the power sector, that we are going really this volatile production there, then the solutions which you were mentioning on the insulation, it might be a bit less speedy. No, I mean you can make very easily, quickly resistance heating or heat pumps, but insulation is probably taking a much more time frame, because changing the insulation and improving the housing, it would take 20-30 years if you go with the rational speed of all this refurbishment. Or it's not true, you can speed it up as well. So the question is on the speed of the change on one side, and on the other side that the consumers can follow this speed, which is reasonable to follow. I don't know if it was clear or not. I mean, the question was that if this solution, like insulation of the building, insulations of the building, changing the heating equipment, might take a bit more time than what we foresee as the very rapid uptake of weather-dependent renewables.
I mean, you know, whether it's 100% renewable by 2030 or 80% renewables by 2035, or whatever, I mean, those are, in terms of what you would do today, very similar challenges. Right? I mean, once we get renewables being 50 or 60% of the annual energy production, you're dealing with the challenges you're going to have to deal with. Now, what Germany's percentage is a little less interesting to me, because Germany, of course, is part of a larger interconnected system. The much more important question is, what's the percentage of variable renewables penetration in the Central and Western European grid, of which Germany, or at least part of Germany, is a part. You know, these targets are interesting. We'll make progress towards them as we can. As you say, you know, progress on improving building performance, building efficiency performance is going to be slower than other progress. Then again, you know, up to a certain percentage, and Bernard can speak to this better than I can, up to a certain percentage of penetration, you can probably get almost all of what you need in terms of demand flexibility from the industrial, commercial, large commercial, and even small commercial and large residential or specialized residential sector. And, you know, making, you know, 100% of the housing stock flexible loads, heating loads, that can wait. How quickly we develop, you know, the ability to produce hydrogen and convert thermal generation to be able to burn it is another factor. I mean, I know the major manufacturers, GE, Siemens, are all now promoting commercial combustion turbine technology that can burn hydrogen. So they're well ahead of the curve. Electrolyzer technology is going to have to progress. At the moment, you know, and there's been a lot of talk of dramatic improvements in the economics of electrolyzers. We'll see how fast that moves. You know, there's a big, first of all, when you say 100% renewables, it's not 100% variable renewables. There's a lot of hydro in there. There's some biomass generation. But you know, there's a very big difference. I'm not going to get into whether the 100% target is the right target or the wrong target. I will just say that there is an enormous difference in cost and operational challenges between a system that is And then, by the way, there's a lot of nuclear in there, maybe not in Germany, but Germany buys a lot of nuclear from France and elsewhere. But there's an enormous difference in cost and operational challenges. And again, Bernard can speak to this, between a system that is, let's say, 97% carbon free and 100%, or 97% renewables and 100% renewables. And the difference is in the system's ability to, on occasion, have access to other sources of supply that may not necessarily be renewable or may not necessarily be zero carbon. And I would be delighted to see us get to 97% carbon free, or not, whatever the right characterization is, whether it's renewables or renewables plus hydro plus biomass plus nuclear, whatever, 97% by 2030. I would be delighted if we could achieve that and maintain the same level of reliability and affordability in the system as we have today.
Okay, just looking at the watch, I might just give maybe the floor to Bernard to have the final points if you want to still raise, and maybe I just make one or two concluding remarks on the presentation, on the workshop. Please, Bernard, if you have any additional things which you would like to, what are the takeaways now?
I think Mike was very good in his summary. Yeah, so I think the percentages that I always remember from my German colleague was in several countries it's still the case. As long as renewable is below 10%, it's you can ignore it. It is a little bit lost in the load, and you don't even look at it, you forget it, and then when you realize you have to do something, it's sometimes too late. Between 10 and 40% of renewable, you really have to start working on it and start managing the imbalances that are created by the renewables. It's not yet a loss of inertia, I think. Yeah, that is too soon. But this is where most of the countries are today, somewhere between 10 and 40%. And then they say in Germany, and above 40% is the real paradigm shift. It's no longer the other sources who try to balance the renewables. The renewables have to balance themselves. So the system really has to change completely. It's set up, and the renewables, I think, together with the variability of the load that we now see, has to manage that all the loads remains covered. So you can no longer count on other sources of power to do that for you. So yeah, this is where we are going. So as I said, it's a big challenge ahead, and lots of great minds are working on it in Europe. I think in America as well. So we hope and we think that we will manage to have this grid with, in the end, 100% renewable. So it should be possible.
Thank you. Mike, you want to say one or two? Then just maybe a few, and I wouldn't call it conclusions because I'm not good at it, and I think you are already nicely summarized what are the key takeaway. What I would say here is that what we learned and what are the lessons from this presentation and from the actually the events which we had learned about is that we see lots of changes. The big changes are coming from this, that the weather would change, so the extreme weather events might come more frequently than before, and we have to include it in the planning process better than before. We see that the future is having more and more renewables in the system, causing volatility on the supply side, which we have to cope with, so flexibility is needed. We might see that on the demand part, on demand side, there might be some increasing volatility, but we see at the same time that solutions could come from that part as well. Quite important and sizable solution to make this balance, because we have to keep this balance in the future. So that's quite an important. And the other lesson or key takeaway is that we have to think a bit outside of the system. So it's not only the power system, but you have to think at the same time the gas markets and other markets, even transport market, the housing and housing insulation. So the whole picture you have to bear in mind. And then this would drive that you need to take lots of action in the processes. Would we do the resource adequacy planning and the actions on the generation side as well, and actions on the consumer side as well? Because what was very interesting for me, and might be a new thing, at least for me, that this question whether mitigation and prevention, would we balance this? It has an economic sense as well, that in countries like and states like in Texas, if you have very rare events, it might not be the best solution to put everything on more than 100% security level over 100 years. You might just plan for a shorter period, which might mean that for some occasions you might have to do mitigation, not only other stuff. So thank you very much for your presentation. Thank you very much for accepting the invitation. And I would like to thank the audience as well, that we had very good questions as well. The whole workshop was recorded, and it will be soon raised on the website. So thank you very much for your attention, and thank you very much for your contribution. Thank you. Bye bye.
Thank you.
Thank you, Ben. Thank you, Mike. And thank you, Susanna. Bye bye.